This is Professor Bronkhorst. I would like to welcome you to this year's Engineering Expo. I am in the Engineering Physics Department in the College of Engineering, and my group, my research group, myself and my students, are called the Theoretical and Computational Mechanics of Materials group. So our department offers 2 degree programs. One is Engineering Mechanics, and the other is Aerospace Engineering. The students that graduate from our department are able to get jobs in many different areas, but many of them choose to work in the aerospace engineering field and work on aircraft, an example of which I show photoed here. This happens to be a new F-35. And so we're going to be talking about some of the things that we study to prepare students to work in areas such as this. This is an example of some of the work that I do in my group. This happens to be a computer simulation of an impact event. This impact is an impact of a plate traveling at 840 miles per hour, or that's 375 meters per second. And what you see in front of you are the sample, which is on top, and the impact plates, which are at the bottom. And this is the stress profile in these plates after the impact has taken place. And 6 microseconds has transpired between the time of impact and the end of this movie. So what we do in my group, mathematics is very important. It's also an instrumental tool that we use to study both materials science and theoretical and computational mechanics of materials. We design, use, and computationally represent materials for applications, many times for loading conditions where the materials are deformed a great deal, and that is a very exciting area. So the work that we do, we seek to develop theories and computational tools which represent the physics of the material deformation and describe them at what's called a mechanistic level or a physical level. And we work pretty hard at comparing our simulation results against experiments using real materials. And so the vision of our group is to offer new approaches to the study and prediction of these complex events taking place within materials. So here's one example. The image at the right is an image of the movie that you just saw. The focus of this simulation was to understand and model damage in metallic materials. And we use things called ductile damage models. And damage in materials is a complicated event which is a combined statistical response of a material due to both loading and the nature of the structure of the material. So most metallic materials are what are called polycrystalline, and they are aggregate composites of single crystals, and typical sizes of these single crystals are going to be something like 50 to 100 microns in general. And so that structure of single crystals for these metallic materials is a very important contributor to how these metallic materials damage under conditions of very high stress loading, the example of which was that impact problem. So I also do micromechanical analysis and study of metallic materials. So the images to the right are a numerical model of what is a polycrystalline metallic material of tantalum, which is an interesting material. So that is a cross-section of a cube, and the length of that cube is 165 microns, and the average grain size of that material is 42 microns. And so each of these different colors in this cross-sectional image of this cube is a different single crystal. And so when we deform that, the stresses inside of that cube can be highly varying. So the red regions are high stress regions, blue are low stress regions. And so that's an important element in determining where damage will form in these materials. And we use mathematics that is coded into computer programs to operate these simulations and to represent the physics of these material behaviors. So these days, additively manufactured materials is becoming very important. So this is an example. So at the far right, you see what's called an orientation image microscopy image of an additively manufactured sample of 316L stainless steel, the kind of material that is going to be pretty commonly found in your kitchen, in pots and pans, or maybe you have a stainless steel stove or refrigerator in your kitchen. So this is the type of material that I've been interested in studying, and we care about how these materials will deform, because if you manufacture them, you don't want them to be failing when you're using them in your kitchen, or if they're used in your automobile or your truck. You want them to be able to perform well and to be tough when you use them. So that's one of the things that we have studied, and of course mathematics is an important part of that. So what you see pictured here are what are called stress-strain curves. And strain is a measure of deformation, and stress on the vertical axis is a measure of force required to deform a simple compression cylinder. And so as you increase the deformation, the force required to deform that sample will increase. Okay? And so that's generally the way in which metallic materials will behave. So another very interesting topic area. So we also consider or work on important materials like titanium. Titanium is a very important low density, high strength material, many times found in aircraft. This is another orientation image microscopy of a sample of titanium after it's been deformed. And each of these lath regions that you see pictured in this micrograph image are what are called deformation twins. And those are special plastic deformation mechanisms that take place in hexagonal close-packed materials, which is titanium, is one of them. And it's an important mechanism by which these materials deform. And our goal here is to understand and model the formation and propagation of each of those deformation twin regions. And you can see this pictured on the right here. So we do a numerical simulation by pulling this sample in tension. We deform it. These twins nucleate at the corners of these grains. They grow, and you can see that we're able to represent the growth of this deformation twin reasonably well, but there's still certainly a great deal of work that we have left. I also am interested in phase changes in materials, and so phase changes are the same as making ice cubes. You take water, you put them in your ice cube tray, put them in your freezer, and they become solid. That's a phase change. That means you go from liquid to solid. You put them in your glass of Coke, and they melt again, and they turn back to liquid, and that's a phase change. I'm interested in studying what are called solid to solid phase changes. And so if you load materials to very high pressures, they will change phase. And in particular, if you load them very rapidly, they will not only change phase, but they will also change temperature. And so that's what is referred to as the thermomechanics of single crystal phase transformation. And you can see examples of these in the pictures here. And of course, a key component of that is good mathematics to enable our numerical simulation of these physical events. So I also care about what's called adiabatic shear banding, another important deformation mode. So this is very common in typical machining procedures. And this is the type of loading event where the temperatures of the material can be raised hundreds of degrees Celsius. And deformation is in very small regions of the material. And this is another form of damage, but without adiabatic shear banding, we wouldn't be able to machine materials for common day use. So another very interesting and very important area for us to study. And then finally, we care about how the thermodynamics of materials transform. So for example, if you're chewing gum in your mouth, every time you bite down on that piece of gum, you're going to increase the temperature a little bit. Well, metallic materials are very much the same way. If you deform them, then the energy that goes in deforming them is going to be dissipated as heat, so they'll heat up a bit. If you deform them a lot and very rapidly, they'll heat up a great deal. And so that's what the term stored energy of cold work is meant to portray. So thank you for visiting. If you have questions, please email me. Or if you would like more information, contact my UW website or my research group website listed here. So thanks again for visiting.